You can get something past it, but you have to do something about it. So I'm going to help you with this. Again, a lot of this class is me showing you things, and you go, oh, okay, yeah, I guess I could do that. What if I wrote this down, square root of x cubed? Are you all comfortable with the idea of me doing this, x squared times x? And then are you comfortable with, if you have an x squared here, I can pull that x squared out, and you would write what? X root x, right? That's what you would do? You all see that? So to get from here to here, we're all comfortable? Okay, go from here back to here. What do you do? How do you get the x in? I put it back in, but what do I have to do when I put it in? I have to square it. It's the reverse, isn't it? Like if I take something squared and I pull it out of a square root, the squared goes away. If I take that and I push it back in, it gets squared on its way in. See, we're used to taking things out of square roots. We're not used to putting things back into square roots. So if you force something into a square root, it gets squared on its way in. If you force something into a cube root, it gets cubed on its way in. And so on and so forth. So what I need, remember my goal is to try and get a 1 over x squared in there, right? That's what I want? A 1 over x squared. But I need to start on the outside. So what can I put out here that when I push it in, it's going to become 1 over x squared?
1 over x.
Just 1 over x. 1 over x here, and 1 over x here. And that way when it goes into the root, it gets squared, it becomes the 1 over x squared. Does that make sense to you? So now limit x goes to infinity. Let's distribute, because that's what's happening up here. What do I get up on top? 5x over x, so the 5 is just left. And then 1 over x times 1, so 1 over x all over. Let's go ahead and push this in and square it, and then we'll deal with it in a second. I push this into the root, it gets squared on its way in. You square the 1 and the x. And now I'm going to do the distribution of that through the parentheses on the next line. Let's see here. Well, hold on. I'm gonna ask some people here. I need to pass this out so people can sign in. So please do. Just initial that you're here. Melina, any idea? I haven't picked on you that much this semester. So. What do we have here? Here to here, here to here. What are we at? If you distribute through. What is 1 over x squared times 4 over x squared going to do?
No, multiply?
Mm-hmm. Just multiplied.
Yes.
What do you get?
4 over x to the 4th power.
Now remember, this is like a 1, so it's straight across.
Yeah.
So what happens?
4x squared over 4x squared, and then the x cancel out.
4x squared over just x squared. You said 4x squared again. You're going to have 4x squared over x squared. The x squareds cancel out, which leaves you with?
Sorry?
Which leaves you with?
4x.
4.
Oh yeah, 4.
4.
Plus. 3x
Over
over x over, yeah.
x squared. And then one of the x's cancels?
And it would be 3x.
3 over x. That's what we get. Now let x go to infinity. What would happen? This goes to what? 0. 1 over infinity, 0. This one goes to 0, and everything else stays. So you get 5 over root 4? 5 over 2. Any questions? Yes?
When you plug in there and you for x,
Okay, so going back, what I'm going back to is this right here. This 1 over x to the n. If you have a ratio where you have a constant on top and the bottom gets huge, it's going to go to 0. So this right here, once I let x go to infinity, that thing is getting smaller and it's going to basically go away. I'm just going to have 5. And then this one will go away, and I'll just have 4, and then square root of 4 is 2.
okay, yeah.
Yes?
Is that considered like an identity or what?
What?
That's fixed over infinity?
It's not an identity. It's just a well-known limit. It's a limit everyone in Calculus 1 should know. You've got a fixed number over something that gets infinite that has to go to 0. All right. Y'all doing all right? Hanging in there? So we did something kind of like this just now. But we have not done this one. So let's try that, something like that. I'm seeing a lot of you, not a lot of you, I'm seeing some of y'all sitting there and I can tell you're paying like very, very close attention and you're engaged and you're trying to make sense out of this, and that's a great thing. I see others that are just kind of half awake and I get the impression that you're not following me, you're just like, I'll figure this out later, and I warn you, those of you who are just kind of just half in here right now, y'all need to just snap out of it and wake up, and because this stuff just keeps coming, and it's the algebra, these little things that I'm doing. If you don't understand, you need to stop me. Don't just be like, I'll figure that out later. Now's the time to ask, because if you go home by yourself and you don't have anyone to ask, you're just never going to get through it, probably. Can't say never, but so. It's very easy from this perspective to look out and know who's here and who's not, like in this right now. I don't want to call anyone out. All right, so what's happening here? Direct substitution. Infinity squared plus 4 is still infinity squared. That's all infinite, right? Minus infinity. What's infinity minus infinity? We don't know. We don't know, right? We just don't know. Now, we did say earlier, right, that we had that one just a second ago where we had like, I don't know if it was like 3x squared minus something x, and we said the quadratic term like dominated this one and we were able to say it was infinite. We can't quite do that here because you can't say this is a quadratic term, can you? It is a quadratic term, but what's it underneath? The square root. So if you take the square root of a quadratic, isn't that almost kind of linear? And you subtract something that's linear, and so you have a linear minus linear. It's really difficult to see which is dominating. Which is dominating which. So we have to do some algebra, some technique. Now what I've been doing the last few problems, we had infinity over infinity, didn't we? And we came through, we looked at the denominator, we find the highest power and try and figure it out. Here we don't have that. Right?
Square it had to be an equation.
Cannot square it because it would have to be an equation.
You do a conjugate.
This you could do a conjugate, and that would be the correct approach. Yes?
Why conjugate?
Who said conjugate? Why?
Because you're subtracting a number from everything that's under the square root.
So you have two terms and a square root?
Yeah.
Okay. So, but I guess you're asking, like, is there something that's like, what's the indicator? Like, how do I know to do that?
Because usually when I do conjugates, it's
A fraction.
exactly a fraction.
Over one.
Yeah, it is a fraction over 1. Yeah, so see, this is why calculus gets tough. This is not, everyone just follow me down this path. And everyone just do what I'm doing and follow me. When you see this, step over it. Everyone's got to find their own path, and everyone's got to figure out their own way. I can't explain why you're saying conjugate. That is just instinctual. It happens to be the right way here. I mean, I can see right now, because I've done thousands of these, that it's conjugate. I know that when I multiply this by its conjugate, the difference of squares is going to work out for me. I'm going to get things to cancel. Right? So I don't know if I'm answering your question. It's just there is no real... Yeah, there's not like a sheet that I can give you like says do this, this, then this, then this. It doesn't exist. Now you said conjugate, but how am I going to do the conjugate? Because I mean, I agree the conjugate would be something like this. And then plus x, right? That's the conjugate. But I can't just throw that there because that's not a 1.
You'd have to do over and over.
Over the same thing? So you want me to put that on top of itself? All right. And see, if people are seeing this for the first time, they're like, okay, that seems insane to do something like that. And then, yes, I could look at that as being a big fraction over 1. Yeah, I mean, I could do that. Now, let's think about a little deeper why this is going to work. This comes down to how much algebra can you do in your head. The more algebra you can do in your head, the further along you can see. See, I know when I see this up here, it's a difference of squares. That's the design of the conjugate is that way. So it's going to be this term squared minus this term squared. That's what conjugate always does. This squared is what? X squared plus 4. This squared is minus x squared. So you have x squared plus 4 minus x squared, which is just going to leave you with 4. So I know the top's going to be 4. The bottom, on the other hand, is what? Infinity plus infinity this time. Infinity plus infinity is infinity. The conjugate took kind of care of the minus part by introducing a plus. So, okay. Limit x goes to infinity. We've got, do all your FOIL up here. You get x squared plus 4 minus x squared. And then the bottom is just 1 times that, so it's just the conjugate down there. And this means you have limit x goes to infinity of 4 over square root of x squared plus 4 plus x. And now that goes to 4 over infinity. And anytime you have a fixed number over something that becomes infinite, that's even on your sheet, right? Anytime you have fixed over infinity, that goes to 0. So this ratio went to 0. Or this limit goes to 0. So in this particular case, infinity minus infinity was 0. In this particular case. But every limit will be different. Our conclusion is not that infinity minus infinity is 0. Okay, so I'm just going to point something out that's in our notes. That if you're ever asked to find the horizontal asymptotes of a function, you're basically asking, how does the function behave at its ends? Then what you're basically going to do is take the limit as x goes to infinity and the limit as x goes to negative infinity. You take those two limits, and that gives you your horizontal asymptotes. Let me give you an example of a function where we can investigate like a horizontal asymptote. Find the vertical asymptotes and the horizontal asymptotes of f of x equals 3x squared minus 5 over x squared minus 25. So when I say VA here, I mean vertical asymptotes, your vertical ones, and then your horizontal are the ends. So how do we find vertical asymptotes? Vertical asymptotes occur wherever your denominator is 0.
So x squared minus 25.
And also, you have to be careful with these. It has to be that your denominator is 0 and your numerator is not 0. If you have 0 on both the top and bottom, that's where you would have a hole in the graph. But in this case, the two answers you get here are what? 5 and negative 5? We have two vertical asymptotes at 5 and negative 5. That's what we've got. Now let me show you, if someone asked you to graph this, what we're saying is that as you come here, the function is doing what? If you look on the x-axis, if you go to negative 5 and to positive 5, right? That the graph is doing what there? It's like going like this, right? Could you actually figure out what it's doing on each side of those? How? Take the limit. So what you could do to figure out what's happening here is you could take the limit as x approaches, how about negative 5 from the left? And wouldn't that be trying to figure out what's happening over here? Of the original function. Can you help me figure out what this is?
Plug it in first.
Okay, so do direct substitution. What do you get on top? Negative 5 squared times 3 minus 5. So what? Positive number on top?
Yeah.
So this is going to a positive number on top. What's the bottom headed to? 0. And I don't know. See, the reason I'm not calling on people is because most of you are like, seem to be okay here. I mean, as far as paying attention. So who's...
You can draw that number line and put...
Okay, so this is the case where we have infinity, negative infinity does not exist. So we draw a number line. We're approaching negative 5 from the left. A number over here, negative 5.001. Plug that in right there. What happens? Negative 5.001 squared. Little bit bigger than this, right? So it's positive. So this is positive. So what's happening? It's going to positive. I know if I graph it, it's going to look like that. What's going to happen if I come in on the other side? So if I change that to a plus, the bottom will be negative, right? So it'll come in on, and when I graph it, it'll look like this.
That does not exist if you have both sides.
Now, if you were just asking what's the limit as x approaches negative 5, it would be does not exist. But if I'm trying to get an idea of what the graph is doing, I know to the left of it it's going up and to the right of it's going down. And then I can do the same thing at 5, right? Just replace this with 5 and do the whole process over again. What would it be if I plugged in 5? I believe it's, should I write it out or?
Yes.
Yeah. Is it opposite? Limit x approaches 5. Let me come from the left side first. Of 3x squared minus 5 over x squared minus 25. We know the top is a number. We know the bottom, well, the top is positive. And we know the bottom is headed towards 0. Take a number to the left of 5, which is 4.99. Plug that in. It's going to be negative. So it'll be negative, which means that over here it would be going down. And then on the other side it would be opposite, so it would be going up. Right? Now, what's the end? Yes?
Okay, so you got the vertical asymptote,
Mm-hmm.
and then from there you're just gonna take that number and find out the limit of that.
On both sides, if I want to know what the graph looks like.
Are you gonna ask for?
Well, you should be prepared to do it, because this is an application of the limits we were doing earlier. This is just showing you how it's tied to the graph. Finding vertical asymptotes, all they're really asking for is where do these occur. But if you want to know the behavior, you have to do this. So be prepared to do all of it. Yeah. Now, what about the horizontal asymptote? That's the end behavior, right? That's what's happening towards the ends. So if I want to find the horizontals, what I need to do is take the limit as x goes to infinity of this function. And we just did this, right? We just did this? Infinity over infinity. And so you would look at the highest, we didn't do that exact example, but we have infinity over infinity. And so you look at the highest power of x down here. Thank goodness there's no square root, right? So I don't have to worry about any magic trying to push it into a root. So what would I multiply top and bottom of this by? 1 over x squared, 1 over x squared, distribute through. When you do that, just like I did earlier, you get what? You get 3. You would get 3. 3 over 1, 3. So I'm not going to show the work for this because we already did a couple of those. That answer would be 3. So that means on my graph, if I go, here's my x-axis, if I go up 3 units, this is where my function should, that's up 3. Let's see, 0's in here somewhere. Say that's 3. My graph should taper out towards that. Right? That's what it should look like. I just made that function up, so I could probably do a graph of it real quick just to make us feel a little better. Plot, let you catch up with me. What was it? 3x squared minus 5 over x squared minus 25.
So you get a pretty accurate graph if you were to find the intercepts, like x-intercepts, y-intercepts, and all that.
Yeah, your graph would get even better. Okay, hold on. I typed in the wrong thing. I typed in cubed on accident right there. I was like, what the hell? Okay, come on, there we go. There. So the computer is freaking out at the vertical asymptotes. The computer doesn't know what to do, so it draws vertical lines. It's like, infinity, and it just draws a vertical line. So if I filled this in, I could fill this in like this, and I would have that graph pretty good, right? What I'm missing are the x-intercepts. So I could find these. How do you find the x-intercepts of a function? You set the function equal to 0, right? So I could do that, and then I could also find the y-intercept by plugging 0 into the function, and you get the whole graph. And in college algebra, you probably did graph rational functions. Probably. So you're familiar with it, but the limit idea is different. In college algebra, I don't think you did the limit idea of horizontal asymptotes. You did more of like 3 cases, usually. All right. I have a sufficient headache. I don't know why I have a headache. Okay. Making sure I've covered what I want to cover here with this section. How about this one? Limit x goes to infinity x to the 2/3 minus x to the 3/5. What's that? Anyone need to sign in? Everybody has had a chance to sign in? Okay. Oh, you need over here? Okay. Any ideas? Two-thirds is larger than 3/5, so the intuition is that that should grow faster, right? I agree. That's a good approach. I mean, a good logic behind that. But overall, we have infinity minus infinity, right? So we need to somehow justify this a little bit. So I'm more showing you this to show you how you can play with these things. If you have infinity minus infinity, we already saw that you could do conjugate, right? That worked. This one, conjugate, not so much because it's not a square root. And that's what the conjugate helps us with, is the square roots. So I like to always say if you have infinity minus infinity, you can always try and turn it into a product, like turn it into multiplication. Because even though we don't know what that is, we do know what this is, right? And we also know what this is. So multiplication of infinities is not a problem. Subtraction is. And we also know what addition of infinities is, right? So all those we're good with, but that's not okay. So maybe I can turn this into a product. Well, the actual method of turning a sum or difference into a product is called factoring. So can I pull out a common factor?
Yeah.
X.
Yes, but they're not x's. And like if I had like x cubed minus x, I could pull an x out.
Can you get a common denominator to put x in that?
Yeah.
Okay, so that's exactly what we're going to do. We're going to rewrite these fractions with the same denominators. So what's a common denominator of 3 and 5? 15. So you can rewrite 2/3 as what? 10/15. And you can rewrite 3/5 as how many 15ths? 9/15. Now, what do they have in common? 9/15. 9/15. So let's see if you can follow this. Watch me do it first, and maybe that'll help. X to the 9/15 is what's coming out. What would be left? So x to what here? 1/15. And then minus 1. See if you believe that. What's x to the 9/15 times x to the 1/15? Add the exponents, x to the 10/15. That's this. What's x to the 9/15 times -1? Well, it's negative x to the 9/15. That's kind of clever, huh? Any questions on that? What does this head to? Infinity. But now what? Times infinity minus 1. Infinity. Infinity times infinity is infinity. So that agrees with what you thought. This was the higher power. But this is just showing you how you could actually work through it algebraically and show it. So this is just another trick of algebra you need to be prepared to use. The answer is infinity.
So how did you get the fractions on top again?
I said I need to turn this denominator into a 15. I looked at 3 and 5 as a common denominator. So 3 and 5, 15 is a common denominator. I said I need to turn that into a 15, so I multiply top and bottom by 5. I need to turn that into 15, so I multiply top and bottom by 3. And then from there, I was able to pull out an x to 9/15. So this has 10/15 in it, right? This is 9/15. What do they have in common? 9/15. What do we got time-wise? 9 minutes? The last example, we're going to call it a day, and we're a little bit behind, all right? But it's all right. We're just going to have to keep plugging along. Where's that sign-in sheet real quick? I want to make sure I cover the stuff that's on this homework. All right, yeah, this will be the last one. Draw a function with these characteristics. I'm going to list a bunch of things now, and we'll have about 5 minutes when I'm done to graph it. First thing, I want the limit as x approaches -4 of the function you draw to be equal to infinity. So we're going to draw a function that has these properties. So everyone's picture is going to look a little bit different. We did something like this before, didn't we?
Yeah.
Okay. I also want the limit as x approaches 0 from the left of the function to be 2. I want the limit as x approaches 0 from the right of the function to be equal to -infinity. Oh yeah, it's going to be kind of messy. I want f of 0 to be -2. I want the limit as x goes to infinity of the function to be equal to 1.
Is this a quiz?
No, we're going to go through this. I'm just writing out all the things I want it to look like first. And then I want the limit as x approaches 2. Yeah, of the function to not exist. There we go. It's good enough for now. Everyone got it? Okay. Did you say Snapchat? All right, you ready?
Yeah.
Here we go. I'm going to draw this. Everyone's picture is going to look different. Start with an x and a y axis. And let me try and start getting the pieces of information together. So here's x. Here's the function's value is the y-axis. And the first condition is that as we approach -4, from which side?
Both.
Both sides? That I get what?
Infinity.
Infinity. So what's that going to look like?
2 going up.
2 going up like a funnel. Okay, at -4, right? So I go to -4 on my x-axis. And I have really like a vertical asymptote there, don't I? And the function is going to go to infinity from both sides. Why is it from both sides? I didn't put plus or minus, right? Okay. So I know that much. Yes. Uh-huh.
Why are you starting, is there a particular reason why you're starting so high from the graph, other than the F0 is -2?
No. You mean like why I started with the red way up here, not down here?
Yeah.
No, I'm just, I have that much board, so I just put it up there. Sometimes you might draw these and have to like realize to make it all come together, you might have to erase and. All right, so that's the first condition, right? That's part 1. Part 2, the limit as x approaches 0 from the left of the function needs to be 2. So what should I do there? Someone volunteer. Yeah, what am I going to draw here?
Would you draw a circle at 2?
A circle at 2?
Like an open.
At 2, what do you mean by 2?
0.
To 0 to, yeah.
Okay, so 0 on the x-axis, and I go up 2 on the y-axis, and you draw an open circle,
Yes, sir.
and I'm supposed to be approaching, though, from which side?
The left.
So I should probably draw a little tail off this side like this, right?
Yep.
So that means as I approach 0 from the left, I'm approaching 2. Everyone agree? Okay, what's the next condition? As I approach 0 from the right, someone else give me this. Raise your hand if you want to volunteer. Someone else, though. Go ahead.
As you approach 0 from the right, you're going to be going down
Down.
on the graph.
Okay, so down to infinity, so something like this. And it's pretty much another vertical asymptote like that. So that means you approach 0 from the right, you're headed off to negative infinity. Okay, who wants part 4? Someone else, though. There.
Be on the y-axis.
Uh-huh. And do what? Just fill solid dot? Okay, that's correct. And then who wants 5? Go ahead.
So wherever it comes from, it's going to go to, all the way on the right, it's going to go, end up going to 1.
So 1 unit high? So like here's 1 unit high, out here somewhere, and I liked the way you said that. Wherever it comes from, I don't know where it's going to come from, it's going to wind up here, getting closer and closer to that line. So it could come in like this, or it could have come in like this. It could have done a lot of things, but that would be sufficient for us to do that, like that.
What we still call asymptote of 1?
What's that? This is 1. Horizontal asymptote at 1, because as we go to infinity, the function's getting closer to 1. That's your question? Okay. And then what about as x approaches, who wants the last one? Last one's probably the hardest.
There's going to be a vertical asymptote at 2.
You want to do a vertical asymptote at 2? Like this?
And when you like
And then what do you want?
Right.
You could do opposite directions. You can make it go to infinity on one side and negative on the other. I could do that. That would definitely make it not exist. So how about, I don't know, I'm going to be fancy with this. How about like this? And then now that I've got an idea and I'm on my last piece so I can start putting it together, how about making this thing go like this? So does everyone agree the limit does not exist at 2? Yeah, that's it. You could do it that way. That's not necessarily the only way, though. What I was thinking of doing was a little different. I was going to do this. This is just the way what I wanted to do. I was going to do this just for fun. I was going to come in like this, and I was going to go like that. Because it wouldn't exist. Remember the oscillating forever wouldn't exist? And then on the other side, I would do something like this. Or I could oscillate in over here, too. Or I could even come up here and oscillate in like this. Because from each side, does not exist, does not exist. Okay, sorry, I shouldn't say. Does not exist, does not equal, does not exist. So like infinity and infinity together, we would say that limit exists, doesn't it? Because infinity, we're saying are going to the same place. But does not exist craziness does not equal does not exist craziness.
You cannot, how do you say, intersect the vertical asymptote?
You can intercept the
Like, for example, if that line,
this. We out of
that
time?
was
Oh,
about
I'm out of time.
the bottom.
Mm-hmm.
For example, if I go like this, like just crossing it,
Oh, if you cross it,
yeah, can you do that?
well, then the limit would exist. Because if you cross it, you're free to go. Try your homework for 1.6. Okay? No, wait. Yeah. 1.6. We're going to have to knock the continuity out as fast as possible. So focus on homework this time. This homework section is extremely important that you get through it. All right? You don't turn in the homework. Nope. If I had time to grade it, I would. If you want your quizzes back, they're up here. I have all your quizzes from last time. You're free to come pick these up.
Take-home quiz.
Yes. That was the one you told me about, right? Yes.
Monday, I was actually